Hello. In this video, we are going to uh, go through some problems, working through the problems, looking at solutions um, for a few sort of examples relative to the material from Unit 1.1, identifying linear systems, thinking about what linearity means. Um, uh, I strongly recommend in watching this material, in following along, that you pause your video when I present each question. Spend some time trying to solve the problem on your own, and then continue to look at the worked solution rather than simply watching how I solve the problems. You will learn much more effectively if you take the time to try to work some of them out by yourself and use my answers as a check on how you are understanding it rather than just as me presenting information. What we're going to be doing through most of the problems we're going to look at here are of the same general form. Classifying a system as either linear or nonlinear, and explaining your reasoning. So, the first problem presented here, the system of equations here. Again, I recommend that you pause at this point, write down your answer or think about your answer before continuing. I won't give this reminder for the remainder of the problems. This system is a non-linear model. What we can see in this is that problem is that there are multiple nonlinear variables. We have x squareds, y squareds present. Those variables make the problem a non-linear problem. Our nonlinear model, nonlinear system. Second problem. Is this system linear or nonlinear? This is a linear model. All of the constants are of the general form of a constant times a variable, 2x, y, x, 2y, constants of x on the other side. All of these are linear terms. It's a linear model. Third example, is this system of equations a nonlinear or a linear system? This is a nonlinear model due to the presence of trigonometric terms, sine x, or sine theta, cosine phi, sine 2 phi, tan phi. Nonlinear terms, therefore a nonlinear system. What about this system? This system might throw you for a little bit of a loop. It is a linear model. All of the terms in this are linear terms. They're either a constant, 2 or -1, or of the general form constant times variable, 3 times theta, theta, phi, 2 phi. It does not matter that we've chosen to use Greek letters to denote these variables rather than x and y. The rule for linearity still applies. Constant times variable is a linear term. certain classes of models, it's very common to use Greek letters rather than um, uh, uh, um, the Latin alphabet for um, uh, for variable names. Doesn't really change anything about how we work with it. Moving up in size, those were all two-dimensional systems. Let's think about some larger dimensionality problems, linear or nonlinear. This is a linear model. Once again, all of the terms are of the form of a constant or a constant times a variable. Constants on the right-hand side, each term with a single variable on the left. You might have looked at this system and said, there's something wrong with this system. If we take a look at these equations, we might note that the left-hand side of all of these equations is exactly the same. The left-hand sides are all exactly the same, but the right-hand sides are different. If the left-hand sides are all the same, but the right-hand sides are not different, this system can't have an answer. There's no way we can find a set of x, y, and z that make all of these true at the same time. That is true. This system does not have an exact solution. This has no effect on impact on whether the system is linear or not, though. Linear systems may have a solution, may not. We'll be discussing this in much more detail further on in the class. To classify a system as linear or nonlinear, we only look at the form of the terms. We don't worry about a solution. Another three-variable problem is this linear or nonlinear. This is a nonlinear system because of this term xy, product of variables, which breaks the linearity. Be careful if you're looking through, you want to make sure a system is linear. It's easy to quickly gloss over this and perhaps miss that this is a product of terms. Right? One more example. Again, a three-variable problem. Linear or nonlinear. Here, this is a little bit of a more subtle problem because we're using these values A, B, C. As long as we follow the convention that A, B, and C, which are letters early in the alphabet, are symbolic constants rather than variables, the natural interpretation of this is that all of the terms are linear. Constant times a variable, constants times variable, constants times variable, and so on. A linear system. Moving up in size to an even larger problem, a problem of 4 variables. Is this linear or nonlinear? Again, this might start to be looking a little bit messy because of all of the subscripts, but this is a linear model. Every term in this, oops, I'm not sure what I just did there. All right, well, it looks like I turned on captions and I'll have to figure out how to get them off later. this is indeed a linear model. Every term is of this same general form of A1, 1, or A2, 1, A3, 1, constant multiplied by a variable, x1, x2, and so on. No linear terms, no nonlinear terms, therefore no nonlinearity in the system. It's a linear model. All right. One more example, linear or nonlinear. This is also a linear model. If we look at the terms of this model, all of the terms have this general form of a constant times a variable, constant times a variable, constant times a variable on both sides. Every term is either a constant or a constant times a variable. It is linear. This system hasn't been simplified. We have variables on both sides of the equations, including the same variables. We could find a much easier way of writing this. This isn't in the standard form for a linear system, but it still satisfies all the requirements of linearity. Therefore, it is still a linear system. Okay, that wraps up our worked problems on identifying linear models. The next recorded unit is going to be on discussing how we formulate linear models for real-world problems. Goodbye.